And thank you very much. Most of what Paul said was true. A few things are not. But yes, I'm here tonight from Silicon Valley to talk about smart hospitals know where stuff is. And this is trying to find some common ground between what you're all experts in and what I do for my living on a day-to-day basis. So before we get into exactly the details of what I'm going to talk about, I'd just like to say, well, why am I here? I think Paul's done a pretty good job, but I thought I would share this with you. So if you can see who that handsome guy is on the right-hand side, you can see that probably is Paul. And also we have a guest star here tonight, Ninette Premdas, who's over towards the back there, who by pure chance was able to come and join us tonight. So it's a fantastic reunion for all of us, and we're all very pleased to be here. So that's why am I here? So what do I do at Google? Which I'm sure is the burning question. And I'm a member of the Android location team, so the team that builds the Android operating system and creates the Android open source release. And of course, we also build the Pixel phone series. And in particular, what the group that I work with, and it's a big group, it's almost 100 people at the moment. Surprisingly enough, we have the simple task of putting the blue dot onto Google Maps, which sounds like it should be really easy. But as you'll see by the end of the evening, I think you'll agree that it is not quite as easy as you expect. And I'd like to say that Google is an interesting company. I went to California first in 1991. I joined Xerox PARC, as Paul said. And the interesting thing about Silicon Valley is that all the companies are different in their own way. They have their own culture. And the aspect of the culture is that it kind of is product. So initially I was at a research lab, so it was fairly free and easy. At Intel, with the second company I worked for, I described it as a little bit like joining the army. And everything you did was highly reviewed. If you had a new idea, you asked to create a PowerPoint presentation, and it may take you 6 months before somebody actually agreed to let you start working on something related to it. Maybe not at all. I mean, that's the kind of thing. And it's because they're hardware companies. So everything is rigidly controlled and has a process. And in hardware, if you make a mistake, then basically you have to live with it. When it goes through the fab and goes into the devices, you generally can't change it. So you can sort of see where the mentality comes out. And then I joined Google, and it was like joining a playground. You could do almost anything you want. And the great thing about it was that if you were asked to, well, in fact, the strategy was that you could have 20% of the time to basically do what you wanted. It was called blue sky time. You defined it. And in order to do something that you wanted, all you had to do was go to your manager, say, I'd like to work on this particular idea I've had. And he said, okay, in a month's time, show me a demo. And that's all it was. You had to build something, and you build it and show it. And Google has this philosophy of fail fast. So you do something, if it's no good, okay, throw it away, we'll do something else. And it's very different from the hardware world. And so Silicon Valley, if you look across the spectrum of the hundreds of thousands of companies which are in Silicon Valley, you find all sorts of cultures, and it's kind of like a genetic pool, where some are successful, some are not, and it's all evolving all the time. In fact, the engineers are moving between these companies all the time as well. So it's an interesting experience. So we put the blue dot on Google Maps. What I wanted to talk about is some of the applications of location. And the motivation for it in the context of your work. I'm going to talk a little about the history and why it's hard indoors, particularly indoors. Then I'm going to talk about the mechanics of how you actually find a position, which could be a very mathematical talk, but I'm going to try and explain it in a way which hopefully is very accessible. So you can tell me afterwards whether I succeeded or not. And then finally, the accuracy and security of these systems, which is kind of an interesting way of evaluating them. So in terms of your context, and maybe my impression of this is totally wrong, but you can tell me later on. Hospitals are very big, chaotic buildings with people running around, test equipment, patients, staff, and coordinating all of these things can be very challenging. And I'm told that it's not uncommon to take a piece of test equipment, something which is measuring heart rate, pulse, whatever, and in the flurry of everything that's happening, getting pushed into a room, and then it's kind of lost because that person is in change shift, somebody else has moved on. So knowing all those things would be very useful to do to have in an automated way. And likewise, patients also, some of them wander around, and to be tracked is something which is probably very useful to actually know where that patient is, even though they have basic barcodes. There's nothing which is actually saying where they are in the building if they decide to walk around. So I think there's a great set of opportunities here to apply location technology so that that technology is made available to the staff to coordinate it all. So if you look at indoor positioning in a more general way, why do we do this? Well, obviously hospitals, definitely, it's a very nice thing to do for the community if we can do that, but there are many applications of indoor positioning. So on the left-hand side, you can see in the public domain, we would have things like retail environments where you perhaps you go into a big supermarket and you search for the chips and the chutney and something else that you want for a particular party. Why shouldn't you just put them into a list and then it guides you around, perhaps visually like this, or perhaps on a map as in that second column, they're showing you where you are and where you have to go. And it can also be very optimized. So for instance, you might want to find things in the order which allows you to walk the least distance around the store. That would be very, very helpful. From the point of view of the store, also having the analytics of where people are and what's happening within the store, where the people spend most of the time, is also very useful from their planning perspective. And in the enterprise, so companies like Google, big companies, just being able to track assets, to provide smart services which are related to where you are. So we talk about these as context-aware services where information is brought to you depending on your location. And then there's a whole series of things which we call proximity, but it can be served by location as well. So you can think about these as social applications, perhaps where I am near you, and so I can share information. So perhaps on a social level, it would be I can share photographs simply because I'm near you. So I come near you and then something pops up which says like you can share if you want to. Another example is there's a lot of IoT applications. So for instance, we have smart speakers now, and you might, in a very human way, say, turn that light on. Well, the system actually doesn't know what light they're talking about, but perhaps the light which is the closest light to you is the one that you really mean. So it's a good bet on what you've done. And if you reinforce that with the light goes on and you're happy rather than changing your mind later on, then again, it learns that if you're in that position, you're probably talking about that light. And then there's applications which are related to security. And this is a good one because I think we've all experienced this, is that in a corporate environment, you can't really leave your laptop. So if you're close to your laptop, you want it to be open. But then, if somebody comes by and talks to you and you haven't pressed your keys for a bit, it locks up and you have to go through the process of unlocking. So you want to be able to keep that thing alive while you're in front of it to avoid going through this laborious cycle of re-unlocking the PC. So we can do that again with location. If we know you're there, we can keep it live. And if you walk away, then it can also naturally lock after a period of time. So location can be applied in many ways. And then also we'll talk about this thing in a minute. So I'm talking about Wi-Fi and its use for indoor positioning. That Wi-Fi itself can self-locate where Wi-Fi is. So if we talk to the big Wi-Fi vendors like Cisco or Aruba, I think also Huawei in Europe, then the access points themselves are often put into buildings, and very soon the building managers lose track of where some of those are. They end up behind false ceilings and so on. To have the access points actually figure out where they are, and when you want to maintain the system, then you can actually send somebody to the right place. If there's remodeling going on, you automatically know where that is. And they can do this by ranging, finding out their distance to each other, and then reporting that back. And then you can figure out the topology of where those access points are. And that's also generally important for positioning in itself. So in terms of a hospital, I think indoor navigation is probably a really big one. Finding people, places, and things I mentioned, but the thing aspect of things is just a little bit different, and I'll talk about this at the end of towards the end of the talk. And that is that typically finding people, we would do that by finding a phone which they're carrying, but something like a walker, for instance, translation.
Zimmer frame.
Thank you. Is more challenging because you can't strap a phone to it. So you want something which is really lightweight and tiny, which you can embed into the walker. So a tag of some kind, which is electronic and advertises its position. So that's another angle on this, is where things advertise themselves. Now, in the Android world, we are very concerned about privacy. Despite what you may read in the press sometimes, we are actually very concerned about providing you good privacy and protecting your privacy. So when we build these location systems, we don't advertise this information to the surrounding that you're in. It all ends up on the phone, and the phone then communicates with the cloud, and we can protect that information there. So no human reads it and sort of sees where anybody else is. But we only do that also if you personally want to improve the location system. So otherwise, it's all contained on your phone. But when I talk about locating objects, if I want to locate a Zimmer frame, then I would put a tag on the Zimmer frame, and the Zimmer frame would tell the environment where it is, which is a different thing. Okay, so that's kind of the spectrum. Location-based security. Another good one here is things like in the US, I'm not sure we call it, in the UK, we call it HIPAA information, personal information, which is restricted to certain people. You might make sure that they can't access that when they go home, where it might be accessible to the family or other visitors. So in a location-based system, you could ensure that the laptop could only access the information when it's within certain areas of the hospital, for instance, and perhaps even right by the patient in some cases. Contextual device control, equipment, inventory management I think are relatively straightforward. So this all seems good. It seems like, yeah, I'll buy that. So why is it hard? Because we've had systems in our cars for a long time. We've had the GPS system, which is usually called SatNav, and we can create maps of the whole of the world, and we can show, a car, you want to go to a certain destination, we can show you a route. If you go off your route, then it recalculates your route to show you where you are, and it's pretty accurate. You look at it. The accuracy is about 3 meters in reality. And a lot of what you see, which looks more accurate than 3 meters sometimes, is because they use snap to route. So they're snapping a position to a route, and they're using some statistical techniques to make sure that they can put you on the right road. Occasionally you see, like, if you have a frontage road along a freeway, it will jump to the wrong road. And that's basically because of that kind of error going on in the system. So why is it hard to do that indoors? Well, the satellites don't go through the roofs of houses. So you can't receive the satellite signals, which are very, very weak signals. And in fact, if you had a receiver and you looked at an oscilloscope to try and find out where that signal is, you wouldn't be able to see it. It's so low signal strength that it's right in the noise. And the only way you could find it is by knowing a pattern, a unique pattern that each one of those satellites is producing, and you correlate, you basically do some signal processing, and you find out where that signal matches into all this other random noise that's going on. So it's very hard. And the bottom line is it's impossible to do that inside the building. So what's been done up to now is that typically the Wi-Fi systems, which were designed purely for data in the original form, so that you could access the internet and have a laptop like this one connected to an access point, at some point, somebody realized that, the further you are away from an access point, the signal strength is getting weaker. So if we look at the signal strength associated with each access point, then we can kind of build this heat map of when you're close to the access point, then we're getting a stronger signal. When we're farther away, and if we do that to 2 or 3 at the same time, then we can get an estimate of the position. And it sounds all very reasonable, but as you can see from the right-hand side here, signals get attenuated when they go through walls. They reflect off objects, and there's something called multipath, where there's several paths through from the transmitter to the receiver, And when those signals recombine, you might remember sort of interference effects that you remember from the physics lab, that when crests coincide, then you get constructive interference. When they are 180 degrees out of phase, you get destructive interference. So the signal strength isn't really representative of what you have to deal with. And in fact, if you were to take a room, it may be even a room like this, and you have an access point which is in the center there, and then you use this color code to show you what the signal strength is from that access point, green being the strongest, red being the weakest. You can see that as you move across, the phone on the left-hand side is at the transition between green and red, and so is the one on the right-hand side, but it's twice as far away. And so this is inherently the problem with using signal strength. It's not a great solution, and we call this non-isotropic. So it's not increasing or decreasing from that access point in a linear pattern going from the center. So we have to find another solution to that. So over the years, I've worked on various things, a little bit of an interlude into history, which has attempted to solve that problem in different ways. We'll come back to Wi-Fi in a minute. But originally at Cambridge University, about the time when I met Paul, I was working on something called the Cambridge Ring, which was sort of an old-fashioned version of Ethernet in some ways, in the sense that it was a good technology, but it never caught on the way that Ethernet was. But we built what was called a private branch exchange on the Cambridge Ring, which basically means we put telephones on the ring, and the telephones use the data network to send voice as well as data. And so now we had a system which was a smart system, and we wanted to have it so that as people walked around, the right phone on the right desk would ring when that person was close to them. So for that purpose, we created something called the active badge. In fact, this was something I did as I transitioned into Olivetti when I finished my PhD, which wasn't exactly on this topic. And the active badge was something that you wore, and it was rather like an infrared remote control. And you can imagine that you've each been assigned one key, and you press it periodically as you walk around. So the detectors which were in each room would detect which key it was hearing, and so it would know which person is there. And you can see the little map at the bottom there was a graphical representation of where those people were. So it's like, for Harry Potter fans, it was like the Marauders map. And we had all these little icons of people walking around. So this is a real thing. It is a concept. And it was turned into a product by Olivetti for a while. But then, of course, cell phone came along, and kind of that concept became obsolete, because you wanted to call somebody, you didn't need to find the nearest phone, you just call, thank you, appreciate that. You just called their phone. And so I kind of lost interest in location for a bit. And at Xerox PARC, I then worked on some other mobile concepts, sensor-driven computing, which you see, when you turn your phone from portrait into landscape mode, and it automatically rotates. We did a whole bunch of early things before that was ever part of products. And then later on, I was involved at Intel with Jim Kardec, who I had great privilege to work with one of the inventors of Bluetooth. So he's quite a character, and you may wonder why was this ridiculous radio called Bluetooth, and it's because he was a history buff, and they came up with all sorts of things like auto wireless, and I know some other very, if you like, engineering terms for what Bluetooth could have been. And it turned out every single one of them was copyrighted in some country that they wanted to launch it in. Maybe in one country it was okay, but not globally, which was the objective. And so one of them had given Jim, who was a history buff, this book about Harold Bluetooth, who had unified all the countries of Norway and Denmark and Sweden with his wars and battles and so on. But he made it into a coherent country. And he thought this would be a great idea. And all the marketing people said, Bluetooth, it will never catch on. But they agreed to keep it as a temporary name until they found the copyright material. So, of course, it stuck. And that's why we have what it is now. So that was my work at Intel. And then when I joined Google, I had the opportunity of joining Android, which was now the up-and-coming thing. It was my opportunity to work on something which is not, if you like, bespoke solution to positioning in something which was basically dying out, the PABX or the local PABX concept, but on something which was now growing in size. And Paul talked about how many computers in the world. There's not 5. I wouldn't like to say how many laptops there are in the world, but I can tell you that there are 3.3 billion Android phones which we detect in our analytics every well, I'd like to say every day, but certainly in a month cycle we can detect 3.3 billion phones, and that's growing every year. And that doesn't include Apple's iPhone, so that's just the Android phone. The Android phone is something like and obviously lots of models, lots of different companies making hardware. It's something like 87% of the market, I think, somewhere around there. So it gives you some concept of what the opportunity is. Because if you write a single piece of code as an Android engineer, then it will get deployed on that many phones. So you have tremendous power, really, in order to try things out. But that, although I joke about that, it's also very exciting because anything you do can be used by all these folk. So obviously, what can I do personally compared to the thousands of other engineers who are working on Android? So I started working on something which I was interested in, which is Wi-Fi standards, in order to create an indoor solution which wouldn't just work in a few buildings where we created this bespoke hardware, and it would be applicable to all the phones. And just to give you an idea of how big or how many different technologies have been used to solve the indoor positioning problem. In the past, people have used ultrasonics. They've used infrared, which I talked about with the badges. They've used stereo cameras in rooms. They've used magnetic coupling, which you can think about as a long NFC type thing, using magnetic tags. They've used IMU, which is inertial management unit odometry, so basically tracking your walking and aggregating that information. All these things have errors, or the cost is wrong. In other words, it doesn't scale to large numbers. RFID tags, I'm sure you're familiar with. You can imagine RFID tags in badges, again, in wallets, and then scanners on doors. But to put that many scanners in and wire them all up and so on, very expensive. Radio RSSI, I talked about the problems with that. And we come down to the very last one, which is the basis of all the rest of the talk tonight, which is radio time of flight. Okay, so we'll get into what that is and how you use it as we go forward here. So now we get into an area which I didn't think I'd have to explain, but Paul explained to me that the word I'm using here didn't quite match with his understanding what standards mean. So perhaps, Paul, you could say in a word what standards mean to you.
Or your standards, or the standards.
As you interpreted it this morning.
A sort of level, a set of rules or quality standards to aim to on your work, for example, like the NICE guidelines, a set of standards that we could aspire to reach.
Yes.
Yeah.
So that it's good to know that, because I would walk straight into this problem of explaining it, and you became, what are you talking about? So Wi-Fi standards are basically, and I think this is a good common word, is a recipe of how to build something in a way that if I build it here in England and we have another company that builds it over in America, and we try and join those two systems together. In other words, my Wi-Fi system talks to your Wi-Fi system, that we understand all the messages that are going by and the exact, the pattern of information which is contained, like who it's to, how it's encoded, are all identified correctly at both ends. And I can tell you now, the actual Wi-Fi standard for the whole standard is about 5,000 pages long. Now, I didn't work on a fraction of that, but I did work on this part, which is 11AZ. So you may have seen these letters after 802.11az. So what's all that about? So 802 is a Wi-Fi project, sorry, an IEEE project, which was designated for the Wi-Fi development, which started in around about 1990. And it took them until 1997 to make the first baseline standard. And I think that was probably written in about maybe 20, 30 pages, so pretty small. And the letters which you see after that 11AZ, and point up there we go, 11AZ is a particular amendment to that standard. And this is the amendment which I worked on with the task group. So again, it's about 30 people in this task group, is adding the positioning capability to the Wi-Fi standard. And I can very proudly say that we only added 200 pages in this thing, but it took 5 years to actually get on that. And why does this matter? Well, all the companies who might contribute have the opportunity of turning up at the meetings, making proposals, we vote. Sometimes you're shot down by various arguments. Sometimes they're engineering, sometimes they're political. And you have to battle your way through this. But at the end of the day, you end up with this document which defines exactly how it works. And you hope enough people have looked at it that you can actually have something that's going to be usable later on. So that was March 2023, which we did that. And it's actually part of a series of amendments. So there was 11MC, which you read certain documents over here about, which is a slightly older version, but it was relatively primitive compared to AZ. And then there's a new one, which will begin to hit products in about probably about another 18 months, called 11BK. And there's obviously a progression of capability, which I'll allude to as we go through this. So first of all, I would like to give you a little video just to show in real time what we intend to do here. So if this works. Okay. All right. Oh, for some reason I'm not seeing what I think I should be seeing. Let me just try something real quick. Okay. All right, there we go. And if I select this. Okay, so this is indoor navigation actually in action. And what you can see here, I'm selecting a conference room that I want to find in one of the Google buildings. And it's navigated a little path from where I am, which is in the top right corner. The gray dot is where the system is estimating I am. But it's snapping to the path. And there, now I'm making a little bit wrong turn to demonstrate this is rather like GPS in a car. And as I'm moving along, and this is 5 times the speed, which is why this is just so that we don't bore you in the audience here. But you can see we're chasing along, and all the time it knows the routes inside the building. And eventually we arrive at the conference room. So a lot of fun to make these things, as you can imagine. So let me just escape out of this, I think. So we knew this would be the tricky part, and I'm trying to manage it right now. So how do I get back? We're trying escape. We've already pressed escape. Oh yes, maybe it needs to be an Alt tab. Yeah, see, I guess it
was down here.
It's the Zoom which is actually hiding it from us. But I think
You go.
no, it's not yet. Let's just try this. Alt tab. Yes. So which one is this one? Okay, so there we are. Okay, very good. Okay, we got one more of those, so we're going to go through this again. Okay, so this concept of time, and why is that? Why is time of flight interesting? Well, when a phone is or any computer is in conversation with the access point, basically these packets of data are sent encoded on RF signals, and you can imagine it's literally like a message which gets sent to the access point, and then or for the access point of the phone, and then back again to the access point. Those messages travel at the speed of light because radio RF frequencies travel at the speed of light. So there's actually a simple relationship between the distance which you'd like to know in order to calculate a position and the distance. If you take the time which it takes, if you can measure the time, multiply by the speed of light, and as typically we're going to measure the time for it to go there and back, then we divide by 2 at the end, and we'll get the distance. The tricky part is actually knowing what the time is that it takes. And let's just assume that we know what that time is for a moment. Then we can actually measure that distance to all the access points which are around us that we know about, or some subset of them. It turns out you need to have 3, but 4 is actually better. And as long as we know where those access points are, and the access points in the 11az protocol can also tell us where they are, because that's actually something which can be programmed into the access point, and therefore tell the phone, you've got this range to an access point which is in a certain position within the organization. And it turns out we can do this using the RF signals at the speed of light to an accuracy of under 1 meter, typically. So how does this work? So the access points that can support this protocol are beaconing their capabilities. So you're familiar with this because when you go into an airport and you say, I want to get on the internet, you find the SSIDs. Well, that SSID arrived in a packet, which is part of that beacon. And that packet also contains a capabilities field. And one of the capabilities is I support ranging. So your phone can detect this. So it detects the beacon. And then the phone will make a request to the access point, assuming it wants to range to the access point, which is the FTM request at the top. And the access point would acknowledge that. And it may be doing other things, like it may be serving video to Paul or anybody else who's in the airport. And at some point, it will then send its own packet from the access point to the phone called an FTM packet, which stands for fine timing measurement. So if you think of this as a ping, and the phone will respond with a pong, and the access point knows what time it sent the message. So we call that T1. On the phone side, it received it at T2, and then it sent its acknowledgement back, the pong, at T3, and it was received back at the access point at T4. This slide is about the most complicated slide that you'll have to deal with today, so I hope it'll be okay. So in terms of understanding this, so we have the total round trip is represented by T4 minus T1. And we have the turnaround time is going to be T3 minus T2. Okay, so if we subtract the turnaround time from the total time, we get the time of flight. But the time of flight is a round trip time. So then finally, we must divide by 2 to get the individual time. And then if you multiply by C, again, as we talked about a moment ago, then we get the distance, which is what we want. So with this little trick, we go backwards and forwards, we can get the distance. Now, a couple of problems. It's not that easy. First of all, nobody has all the timestamps in that scenario. So the way you do this is that you have several rounds of this, and the FTM packet at the bottom there piggybacks on the T4 and T1 that it got on the earlier exchange. So now when the phone gets that packet, it had T2 and T3 because it generated them to start with, and the T1 and T4 arrive, it has all of the information, and it can then execute this simple calculation and figure out where it is. Now, there's another problem, if you're really paying attention. So, wait a minute, how is the clock on the access point synchronized with the clock on the phone? So why is that T1, why does it have any relationship to T2? Why does T4 have any relationship to T3? And the cool thing about this way of doing things is it doesn't have to. And the reason is that you can imagine the clocks would be progressing at the same rate, but one might read 1 o'clock and one might read 4 o'clock. They're not synchronized, but they are progressing at the same rate. So if you subtract T4 minus T1 on this side, which is the total round trip time, then that is a delta time. It doesn't have any absolute reference. It's just the time between those two things. And likewise, T3 minus T2 on this phone is just the delta time. And so it has, it doesn't need any reference to any real clock. So we know the delta time and we know the delta time over here. So when we do this calculation, it doesn't matter that T3 and T2 don't relate to T4 and T1, because they're both the same kind of clock. They may both be going at, a gigahertz, but it doesn't matter what time we think those clocks started. And so that's why it's done as this round trip time concept, because you don't have to worry about synchronization. So that's the real insight. If you've got that, then this is the main thing. And we had to standardize how that exchange is done and how those timestamps are agreed upon and then shared with the devices. So Okay, so now we've got the ranges. You know about the ranges, you know how to calculate them. How do we calculate a position? So now we're going to talk about a little bit of analytic geometry, but hopefully in a way which is very accessible. So the phone is, we know, is a certain range from an axis point. So that tells us that the phone is on a circle around the axis point, somewhere on the circle, but obviously it's in a real position on that circle. But that's how we can interpret it. It's a circle around there somewhere. So if we have, say, 4 axis points, then we have 4 circles where it could be. But those 4 circles, where they intersect, will be the place where that phone is. The hard part is figuring out where they intersect, as always. So even if you're not a big math wizard, you may remember from high school the circle equation is x squared plus y squared equals the radius squared. And you can change the center of the circle by subtracting those x1 and x2s, y1s, y2s, and so on to move that circle any way you want. If you solve those 4 equations, you'll figure out where that is. Okay, so is that easy? Well, actually, it turns out it is easy to solve those 4 equations, but I'll tell you in a moment why it's not relevant. If you subtract any 2 of those equations, all those nasty x squared terms disappear, turns out, for the variables that we're concerned about. So then you end up with line equations. So you subtract pairs of those, and you figure out where the line equations go. So this is an example of a line equation if you subtract the blue circle and the yellow circle. And you can do that from pairs. In fact, you can see another one over here, which is the red circle and the yellow circle. And so you can just see where those 2 lines intersect, and you can Google how to do that. That's quite easy. Now, here's the real problem. We've assumed that all the measurements were correct. When I measure anything, if I take a ruler and measure something, it's rarely exactly what you think you've measured, right? There's some error in it. So the solutions to those equations can never be solved because they don't all have the right parameters to start with. They're close, but if you were to do an analytics purely on those equations, it would not work. And if we go to the next slide, we can see here that these circles are deliberately have been set up so that they won't intersect at one point, but there is this area of uncertainty around where they do intersect. So you actually have to figure out what the best solution is, given they don't intersect in the right place. So there's uncertainty in the position, and we can use some analytic techniques to do this. Now, there are some very mathematical approaches to this, but I'm going to give you one tonight, which is easier to understand. So believe me, this is easy. So what we do is we put a grid, and this grid may be down to say a 6-inch grid as an example, or 150 sorry, a 15 centimeter grid. And we put the axis points onto that grid. And then what we say is, if the phone had been, say, in position, and there we use the example which I've got in here, 22, then I would have measured the distance D1 to AP. But in practice, the phone is actually, where you can see it is over here. It's not here at all. In practice, we actually measure this range. So there will be an error from that one to that one, which is going to be quite large because it's actually nowhere near the right place. And we keep doing this for each of the axis points, and we add up the differences. In fact, for a statistical reason, we add up the square of the differences. And we store that value, the square of the differences, in each of these squares. And what we're looking for is where the sum of those errors is the smallest. And that would then be the grid square, which then most closely matches the measurements which you're going to make. And if you were to do that, and you were to draw, if you were to color regions of error which were similar, you would end up with these contours of error. And then you would put you'd estimate your phone to be at the lowest point in that contour map, basically. So that's how it works. And that's called a least squares solution. And it's a very effective way of finding out what's going on. There's sometimes also rather random noise things. You can apply filters for these things so you don't get so much jitter. But in principle, that's what you do. And just for the record, fortunately, it's a different kind of talk. You actually have to use 200-year-old mathematics. So you use Sir Isaac Newton's calculus and the ability to factorize an arbitrary function in order to find out where the minimums are. But because the minimums all don't occur in the same place and because there's this error, we have to use Gauss's mathematics, which was this least squares concept. And we add the two together in this Newton-Gauss solution, and that's what you really use in the Android system to solve where it is. But it's really just doing the same thing as I just showed you, but it's doing it in a much more computationally less powerful way, in the sense that it's not using thousands and thousands of cycles to do all these calculations. It does it actually in a very straightforward way, and actually it has a lot of commonality with artificial intelligence, because that concept of a minimum or something which is not exact is actually what artificial intelligence does. And we often refer to it as gradient descent, where you've got a guess at what something might be, but it's not optimal, and you follow the gradient down, reducing the error to the thing that you're trying to get to. And that is what your answer is. And the reason this mathematics was invented 200 years ago was actually to figure out where the planets are in the sky. And you say, well, how does that relate? Well, they knew what the mathematics might be, the models of these things moving. But when you have a telescope, which is an 1800s telescope, and other instrumentation which is not very accurate, then all your measurements have fairly big errors. So they would just make lots of measurements and then use math like this to figure out where the planets were. So that's the worst of the talk, I can tell you. So accuracy and security. So what defines the accuracy? So there's this concept of bandwidth, and I don't know whether you've ever looked at your access points at home, but you can be on a 20 megahertz channel or a 40 megahertz channel, 80 megahertz channel. Most of the ones you have at home are likely to be 80. In a big store or in a hospital, they might be closer to 40 because they need to reuse the channels to cover a very large area. And it turns out that increasing the bandwidth increases the accuracy. And you can think about this as if the bandwidth basically, think of it as the how or what the maximum frequency of the signals are that you're using to encode the data. And if you have a higher signal, it's moving up and down faster. So the time resolution, which you can figure out where that thing starts or finishes, is going to be better. So in an ideal world, you want to have more bandwidth and you get more accuracy in the system. And also signal strength matters. And a lot of these protocols, we use packet field repetitions, where you repeat the signal and you add those signals together. The signal adds, and if there's noise on the system, the noise is random and the random cancels. So the signal adds and the noise cancels. So we use packet repetitions, this one. And then finally, there's this thing called spatial diversity. So this is the chart at the bottom here. And here, if we have an access point and we have a client system, if you only have one antenna, then there's only one path really between the two. One's direct path, which is the one you want to measure for distance. But if somebody's in the way, then all you've got is potential reflection. So that would be a multipath, effect, which would mess up your measurements. So what you do is you actually have multiple antennas. And sometimes if you look on your Wi-Fi box, you see something called MIMO, which is multiple in, multiple out antennas. And then the access points often have 4 phones, typically have 2. And then that means you've got 2 by 4, 8 pathways between here. And if some of them are blocked, then others are direct through. And so that's the other secret source of 11AZ, that we use MIMO in order to make this work. So here's this little fun thing that we're going to talk about now. It's like, as soon as you create a system which is useful, there's somebody who wants to mess it up always. So what I'm going to show you now, and I'll be talking through it as we go, and let's hope this will work for us again. So come over here. Okay, we should be running. Yes, good. So what you're seeing here is a car, which turns out it has a wireless car key. And there's a couple of nefarious guys that just pulled up over there. And one of these guys is coming out, and you see both of them have some sort of box which they've got. This is actually from the Midland Police in the UK somewhere. Was it Solihull? And you see one of them is standing by the lock, and the other one is going up to your house, and he's trying to find that bowl that you put your keys in, either along there or alongside. I think he may walk sideways in a minute by the kitchen, trying to find out where you put it. So basically, what he's doing, he's bridged the gap between the key and the car and the key are looking for them to be close enough that it would activate the locks of your system. So this is called a relay attack. And probably not for the kind of car I own, but for high-end cars, this kind of thing goes on, believe it or not. It's worth building the electronics in the system to be able to do that. And there you can see, I think there's a second phase where they realized that I think he initially opened it, then he needed to start the car, and then he went back to do it a second time. And all this was caught on the camera, which is really fascinating. So one of the things to think about, and let's see if I can get back to where I was. I think Alt Tab is probably the trick. If we can get to that. Is that right? Not quite, sorry. No. No. Okay, I might need some help here. If anyone has got a moment. Yeah, by the way, this is a Microsoft PC. I don't work for Microsoft.
Perfectly this morning.
Yeah, it's because we also have the third component, which is the Zoom component.
Yeah.
Okay, so this is getting better. No, this is so we can actually we won't need this anymore. So let's get rid of it completely. So X out that thing at the top. Yeah, and okay, this is good because now I can go through. Okay, apologies. Okay, so the interesting solution is that this ranging technology can help with what you just saw, because although they've created this bridge between the two ends, now if you can measure the range, even though it's going over this relay that they've got, nothing travels faster than the speed of light, right? So it still takes longer. And if you measure the distance between the lock and the key, then in fact, it will be longer. So the lock, if it knows that information, it can decide not to open the lock. And that's basically how you defeat that attack. However, as always, somebody comes up with another smart attack, which defeats even us using location. And so this is just an important last thing to talk about, is you can have an adversary that will sit in the middle that will know about your distance measuring technique and mess up one of those timestamps that we talked about at the beginning. So this is the T4 that we had over here. And what this adversary, this is Eve, which is often a name used for the adversary, is doing is overlaying its own signal on top of the signal just enough to cause that signal there to be wrong. And so that timestamp to be wrong. So how do you deal with that? So obviously, it's a cat and mouse game. You're trying to defeat these people as they come up with these ideas. And so one way of doing it is you encrypt the packets, right? There's a shared key between the two. So if you encrypt the packets, then they don't know how to mess with this timestamp, because unless you mess with it correctly, then the encryption of the entire packet will not match what it's supposed to do at the end. So we're creating a check that the encryption matches what it's supposed to be. And so we think, okay, so that's all you do. We're done. No, there is another problem. And so this is what you call a map attack, which basically means you affect the contents of the packet. But there's another kind of attack, which is called a PHY attack, which is a physical layer attack, which basically means you don't attack the contents of the packet, but you actually attack the signals which you're using to transmit the packet. And this is kind of interesting. So just to explain very briefly, in order to decode the data packet, there's something called a training field at the beginning, which is a well-known sequence of signals. And an attacker can create something called a time advance attack, which sounds like something out of science fiction. How would you advance time? Well, the way that these packets are determined to arrive is that you have to figure out where the beginning of that packet is. And if this is a well-known training field, so it has a pattern which is used then to decode the rest of it, then if you take a copy of that packet and you overlay a stronger version of that a little ahead of this thing, then the electronics which is receiving the signal will see the end of this packet nearer the beginning. And it turns out you can actually affect the thing that's trying to calculate that timestamp. So, damn, how do you defeat that one? That's a time advance attack. And the answer is just at the bottom of the slide here, which is this phase encrypted training cycle. So you actually encrypt the encoding information, and you can use the same key that you use for the MAC address if you want. So now the guy doesn't know, or guy or girl, I guess, doesn't know what the attacker, what to attack this packet with. And all they can do is they can listen to the front of the packet and begin to get an idea of what the phases are. They process like crazy trying to figure out what those phases are, and then they've only got a relatively short time to attack the packet at the end. And it turns out that we figure we've got 10 years with current computing increase before it would be possible to achieve an attack like this. And by then we'll have version 2, so no worries. Okay, so I'm getting towards the end here, and so I've just got a few quick slides at the end, because what I've talked about is phones, and I wanted to just mention tags at the end. So it turns out it's very hard to use Wi-Fi for tagging things, because Wi-Fi is fairly power expensive technology. So you actually need something else. And there's a new technology called ultra-wideband, which has been starting to be put into certain access points. So for instance, Cisco have a whole product line with these access points, which also support UWB. And UWB exists in this form, which it's called TDOA, which is time difference of arrival. And basically it uses a principle of the access points synchronize their clocks so that they all do, in this case, share the same clock. Not the same clock as the phone, which obviously would be a lot harder to get that one to synchronize as well. But what happens is that if you just have a very simple tag that makes an an ultra-wideband signal, which is sent to these devices, then it takes a certain time to get to this guy, and a certain time to get to this one, and a certain time to get to this one. It'll all arrive at a slightly different time compared to each other. But if you take the time differences between them, then you get something which was actually used before GPS. And I don't know if any of you are mariners from the past or something, but there was something called LORAN before GPS. And LORAN was basically a system where you had a master station, which would typically be on the coast somewhere, and 2 other stations on the coast. And these perhaps with cables or some other radio technique, they synchronized their clocks. And then an aircraft, light aircraft perhaps, or a boat could listen to the beacon here, listen to the beacon here, and simply measure the time between them. And if you look on the left-hand side, again, it's basically high school math again. It's like lines which are a constant spatial difference from 2 other points are called hyperbolas. And so constant distance or constant time, it basically amounts to the same thing. So you multiply time by the speed of light, you get distance. So these are all the lines of hyperbolas, which are represented by a time difference. And so just like we did before with circles, if you find the point where between 2 of these, where there's a hyperbola, and there's another hyperbola between these 2, where those 2 hyperbolas intersect is where you are. And I thought this would be interesting to you because obviously with all the geopolitics going on in the world at the moment, you're hearing things like GPS jamming. There are certain parts of Ukraine, for instance, where it's virtually impossible to use GPS. There's jamming going on. So the global system which used this was closed down largely in about 2011. But now companies and countries are thinking about reinstating this as an alternative to GPS when these bad situations happen. So this could become very relevant, and it could actually relate to things in your hospital through the same technique. So just to finalize here, so this is how it would typically work with those lines of or contours of error that I talked about, except we're no longer getting circles intersecting, we're getting these hyperbolas, and I've obviously made that one exact, but they wouldn't necessarily be exact, it would be in the middle there. And that's the math that you need to solve it again. Not for today. Okay, so integration with Android, say, how does Android use all this? Well, we do provide APIs, so application programmers can use this information at the very raw level and create all those features that I talked about. But we also have this thing called the Fuse Location Provider, which is a very, very straightforward system for anyone to use, which you basically say, what's your location? And underneath the hood of this thing is that we look at all these things. We look at GPS, we look at the IMU, we look at accelerometer and gyro, we look at the cell tower information, and we look at Wi-Fi signal strength. And when it's available, Wi-Fi RTT, which I've been describing, the round trip time, and UWB, we're integrating all of that together. This work has been done. The UWB is very experimental at the moment, so it's not part of the system, but it probably will be within 6 months or so. So all these things are integrated, and you just simply say, what's my location? And we'll give you the right answer. So hopefully it'll be very, very easy for any developers that you're working with who actually want to use any of this stuff. Okay, well, that takes me to the summary slide. And so basically I've motivated why I'm here. It's not just about pomegranates. But there's this technology shift in Wi-Fi access points, which are using these protocols for RTT and ultra-wideband. And in some of your hospitals which upgraded their Wi-Fi recently, you should actually have that available to you. And I would say that I'd be very interested in talking to anybody who's very connected with the NHS, who may be, perhaps on the off chance, may be interested in a trial of some kind. Because clearly there's some aspects of this which are experimental, but Google would be prepared to work with any of the hospitals to see how well we can make this work for you. I think I've also talked about the precision, the accuracy, and the security that you'd expect. We can expect to get sub 1 meter is the great thing about this. It's not just the phone, it's on the phone for a long time, but it's the vendors for the access points like Cisco, Hewlett Packard, who bought Aruba, and Cisco is the largest vendor. HP is the second largest. I imagine that Huawei is the third. I'm not actually sure. But this provides a solution so that you can have smart, secure, and precise indoor location in a hospital and solve some of those problems.
Thank Roy for taking us through that there, and there will be a multiple choice questionnaire. Testing you on, and the pass mark is 50% for the supper and
For the wine?
for the wine as well. It's a little bit higher than that, but I'm glad that you've explained a problem I never even knew I had really. But anybody who wants to help Roy find where all this equipment is, where all these patients are, should be willing to collaborate. So my at this point now, I want to ask is anyone brave enough to ask a question? So you can make it general. Yes, we'll take that gentleman there. Yes. Sorry, we're just going to pass the mic for you because able to.
It's a very interesting historical question, which is way below the level of what we've been learning about. But what I would take from this, and I'm sure it doesn't happen anymore, if two health professionals meet in a linen cupboard, they should leave their phones in the sluice.
I think you're absolutely right.
I think that was a comment, an observation on the question. Point well taken.
Yes.
There was another question there. Please, could you pass the microphone across there? Thank you, Judith.
Tree anniversary is called E.
Oh, it's just from the phrase eavesdropper. So Eve listened in on the signals, so she's an eavesdropper on this case. Well, yes, it's phonetic. It's not. Yeah.
Okay, yes. Good. Next question. Yeah, that was an easy answer. Yeah.
I recently read a book called Longitude. Read that.
Yes. Harrison's clocks. Yes.
Yeah.
Yeah.
Big argument between time versus data for working out longitude. You kind of like time versus good signposting mapping in hospital. And I'm guessing you're tuning into the fact that some of the signposting mapping is inadequate in hospitals. But actually, a lot of them it is. But I want to apply our eyes to look at the signposts and maps. And
Yeah.
that deficiency you've identified, then that's the motivation to overcome that.
Well, I think the applications would be slightly different. I mean, I know that there are plenty of people I've met who go into hospital and are trying to find radiology or something like that. And I don't know, perhaps it's just overwhelming in the environment that it's complex, and to have some, go here, turn left. And you often see them asking at the information desk, even though, as you say, there is signage there. So that's one thing. But then there's other aspects which are, I was giving this example to Paul earlier, is that, supposing somebody has a heart attack and it's like, okay, we'll call the cardiologist. Well, turns out that cardiologist, even with a cell phone, is actually the other side of campus, and it's going to take him, maybe 5 minutes or more to get across here. What you really want is the most qualified person who's closest to where that incident is happening. So you could do things like that in order to locate people. And then the example that we had with the Zimmer frame is that the actual, the hardware which you're trying to locate is sometimes not that expensive, but it's essential for particular activities. So to be able to locate things very rapidly with the UWB tagging mechanism, I think would probably be useful. I mean, I haven't had personal experience, but I can relate to that in my opinion.
Application. Thank you.
Yeah.
Very good, thank you, Gus. Another question, Bob. Yeah. I was just thinking, this is Androids. What, and you said, sorry, you said that most people have, 87% of people have Androids?
I think it's somewhere around there. In the world, we're talking in the world.
Yeah, no, it's
Yeah.
funny because
It'd be useful to do a straw poll here and see how many people have Android phones.
Well, I can tell you in the United States, it's 50-50. 50. So in Western Europe, I imagine it's probably in between the two.
So there must be people like you working on the other side doing similar work.
Yes.
And how do you work together on this? Because what's the point of having two completely separate systems, and how do you combine them in the end? Or do you not?
Well, so this goes back to the Wi-Fi standards. Apple attended those standards meetings as well, and they voted and either agreed or disagreed with some of the people there, but eventually we all came down to the same standard. So that's the thing that everyone's going to implement. Now the system itself is just you implementing it, or the OS vendor or the developer implementing it on the phone. So Apple can do that independently, and because of that standard, they will communicate the same packets as if one was the other, or vice versa, right? So that's how it works.
So it's nice to know when I enter a hospital and get completely lost with my Apple phone, it'll still find me where I am.
Yeah. Now there is one thing to say, is that I think Android has a different philosophy, is that we tend to embrace all new technology and we put it out there and create APIs for developers to use. Apple is much more secretive about what they do. And they may not announce anything for a long time, or they may use it and not even tell you that they're using it. So we have to wait and see what they announce in the future. And they have their big developer forums like we do. We have Google I/O. And when they have their announcements, I'm sure at some point when it's appropriate, they'll tell you what they're doing. But I suspect it won't be that far in the future.
But basically what you've done is create these standards, this sort of cake recipe that any provider, both Apple or Android, can use. So you create a common language for everyone to communicate.
Exactly.
But that in simple language, yes, it's
Yeah.
so thank you. You've done it for everyone, really. Yes. How far away are we, might I ask, from implementing Help Find My Zimmer frame? Because I've not got many years left. Did you say, is this theoretical, or is this actually going to happen?
No, I think it's going to happen. So the UWB radio is already in the Cisco access points. So you can probably find hospitals in the UK already. It's there, but it won't be turned on. And the tags are typically it tends to be smaller companies that make things like tags. It's becomes their business, and they're really focused on that business. So I think you'll see a few small companies pop up with these tags. We've seen experimental versions. Obviously it's proprietary information that we have at the moment. But you will see them.
Not long,
Not long.
Yeah. Cutting edge stuff. You heard it first in your medical society.
Yes.
Question. I'm going to take one or two more questions. That lady there, who I seem to remember was in a canoe not long ago. Would you like to?
So, it is. Might be regretting a glass of wine.
That's why I didn't have my glass of wine.
But if I've understood correctly, our science buildings, GPS gives us sub 3 meter accuracy.
About
You're saying indoors we can get sub 1 meter.
Mhm.
But in urban environments, if you're walking down the street, you pick up loads of Wi-Fi signals. So will it not eventually replace GPS outdoors? Or is that
Oh, I
not
see.
possible?
Yes. I mean, you're making a good point. And this is one of the things that makes the fuse location provider in Android difficult to build. Because if you can use all of those signals, or which ones do I use at any point in time? And indeed, we have problems, or we have developed strategies, I should say, problems to solve and strategies which solve them for cars even driving on the street. Because obviously you want that GPS configuration to be working. And in fact, we can detect the activity of car driving, which has these large accelerations and so on. And so there are these modes that exist within the system of actually we have driving, walking, biking, stationary and still. And that biases what technologies are used. So in that particular example, when you're driving, I think it's almost entirely GPS at that point. And the problem with Wi-Fi, particularly when you're using RSSI, is that the system would tend to draw you into a building, so away from the road. So that's the reason. But with RTT, it's a lot more accurate. So even though you're still in your car on the road, we can actually measure that distance much more accurately. And if we do that, then maybe we can use that to enhance GPS and get below 3 meters in that as well. But we have to be very careful, because one of the reasons that it's challenging to work in the Android team is that I might have an idea, I can change that math or change that algorithm, but then it gets pushed into all your phones, and 3.3 billion people, even if 1% of them are only having that problem, that's a lot of mad people who send us bug reports. So we have to figure very carefully and roll these things out very slowly. So typically we have these rollout things where you'd roll out to say just Google people initially, and hopefully you get past that, and then you roll out to say 1% of the world population, and then you go to 5%, and then you go to 20%, and then you go to 50%. And at each level you can hit different things, because the Android phones, say in I don't know, North Africa, might be very different from the Android phones which we have. Just because of the economics, they might be a lower end phone. And so the GPS system is not as good. So there's all sorts of things. And that's why there's 100 people working, and that's not just just me. Yeah,
That's good. It's a global perspective. I think it's an appropriate point now to actually invite. So thank you so much, Croy.
Thank you.
Really insightful talk. Really enjoyed it. I'll be studying it closely after tonight. Tom will be available on recording, by the way, in the members area afterwards. So thank you, really appreciate it. I'm going to invite Dr. Bob Adams to formally give a vote of thanks now. So thank you.
Right, well, now I know why Paul chose me to do the vote of thanks. What have I done, Paul? Did you know that I did basic maths and then gave
Oh, is it? Yeah, it's one good that, isn't it? Really. I
Oh,
can see
really?
the way you sound.
Yeah.
Use the
Okay, yeah.
just for your positioning, so the people on
Well,
Zoom know where you are.
like the lady in the canoe, I chose to do medicine and had to do maths. I gave up maths, but had to do chemistry and physics, A level. They were bad enough. Yeah, well, what a fantastic talk. First of all, as I've got an Apple phone, I thought Androids was something with Blade Runner, really. But now I know.
Great camera.
How many people have got Android phones in this room? Hands up.
Look at that.
How many people have got Apple phones?
Oh. Yeah, they're all holding it. I'm proud of some of you.
And now when I look at my phone, it's the blue dot will have a different significance for me. I'm looking for that. Other things I've learned, Xerox PARC. I imagined a park with trees full of Xerox machines. And now I know it's not a park, it's PARC, is that right?
Yeah. And actually, these days it's no longer even Xerox. They spun it off as an independent research entity.
I can't even remember what the Xerox is. It's a photocopy machine. On protocols, my God. Yeah, kindness, oh, that just gives terror into my mind. I never understood it. Yeah, that was it, that was enough for me. Right, so at risk of having a time advanced attack on me, I think I better wind up this voting. Thanks, because we'll all be wanting to finish and go for supper. Thank you so much. Gosh, for this fantastic talk. Roy, well done, Mark. You realise I'm terrible with them. Well, I mean, I have learned a lot actually, and I had to stay awake for every second of it because I knew I was going to get it, and I did. It was really good. I think we'd all like to join up in thanking you for this talk tonight. I'm sure you'd all share my appreciation.